Woohoo! All right, so as with usual, we will start with the pledge. If you're wearing a cover, please remove it. I pledge allegiance to the flag of the United States of America,
and to the republic for which it stands,
one nation,
one
God,
under God,
indivisible,
indivisible, and justice for all.
Wow, that is so confusing to recite like that. I think in the future, I will either have everybody mute or I will remove my headphones when I try to say that because I got lost. Oh, man. And that's recorded for posterity. Okay.
Yeah.
We'll get rid of that now.
All right.
Great.
I'm showing that streaming is running now.
Okay, good. So maybe we missed that. Either way, if it worked, it worked. If it didn't, it didn't. So any visitors first time here with us, let us know who you are, where you're from, and what your call sign is.
So I am.
Hey, Russ.
Yeah, hi. So I'm Russ Carroll, and I live in San Marcos.
And your call sign?
Kilo November 6, Kilo Alpha Oscar.
And 6 KAO. Okay, great. Welcome. Glad to have you here with us.
Thanks.
Anybody else first time at a club meeting?
This is Matt. I'm calling from Carlsbad, KN6JSX.
Hey, Matt. Good to have you with us. All right. Anybody else? And our presenter, of course.
John from Valley Center, call N7MM.
Great, John, welcome. So I was going to ask people.
Us Valley Center guys are ganging up on you. There's two of us.
Uh-oh. So I was going to ask people to please change their name to their first name and their call sign, as many people have done. But I'm trying to figure out how to do that myself, and I can't figure it out on the mobile device where to do that. I know if you're on a computer, there's the three dots in the corner. But
I think if
on a mobile device,
if you're in a gallery view and you click on your own image, that it might give you a chance to change that.
no, it just pops up the meeting controls, and then there's a more.
Go to participants, click on your name. If you're on an iPhone, I'm on an iPad.
Ah, there we go. Okay. Thank you. Okay, so I will rename myself.
I'll try and do this while driving per Joe's instructions.
Don't do that. Okay, there we go. All right. Any other first-time visitors that we didn't talk to yet? Okay. Great. Anybody recently upgrade their licenses or get a license?
So I did. I just passed my technician exam like 2 weeks ago, and so I don't know anything. I mean, that's
well.
I'll start off by saying that I haven't even made contact with someone on the radio.
What do you have for a radio?
I have an ICOM 7300.
Okay.
And I realized that I'm studying for the general now because I just, there just isn't a lot you can do other than handheld stuff, which I didn't know at the time. So I've got a handheld on order that'll come in just to mess around with. I don't even know why I'm doing what I'm doing at the moment. So.
Well, hopefully you will learn a lot tonight about SWR and some of the important things to keep in mind when you're transmitting. So that's something. And then once you get your handheld and you can get on the repeaters, throw out your call sign on the 146.730. There might be people listening, and we'll go from there. But great, welcome to the hobby. Congratulations.
Thanks. Thank you.
I just tested a couple weeks ago for tech in general. Yeah, I've just been playing around a little bit.
Great. I'm being told the kids just went to bed, so I'm going up top to the command bridge instead, so I'm not too loud for them. Okay, any announcements? I know there was an email earlier about something going on this weekend, the Ham Expo.
Yeah, the QSO Ham Expos this weekend.
Yeah, so there's a whole bunch of interesting speakers and topics. The list has been published now. I don't have a URL for that. Keith, do you have that URL?
No, not with me.
Okay. Well, QSO Today Ham Expo, if you Google that, I'm sure you'll find.
Oh, yeah, it's released.
Comment.
Go ahead, Charlie.
If you Google Ham Expo, it all shows up.
Okay, great. All right. Any other announcements from the group at large?
I have one.
Okay, go ahead, Charlie.
I'd like to make sure that everyone knows that the Palomar ARRL scholarship has been awarded. The Lady Ham, her name is Jackie. She's up in Valencia. She's going to UC Berkeley. She is an engineering student, going to pursue engineering in the electronic and computer science world, has a technician license, and you will see all of it in next month's scope. We are very fortunate. Sharp young lady.
Great, thank you, Charlie. Yeah, we had very limited information when we had to publish this month's scope, so we just had her name in there this month, but we have a lot more information. We've actually made contact directly. Charlie has made direct contact with her, so thank you for Charlie for taking that on and running with that, managing those contacts and such.
Hey, Joe.
Yes.
The URL is QSO Today Ham Expo.com.
QSO Today hamexpo.com. Okay, great. Thank you, Keith.
I'll take it right there. Yeah.
Comment?
All right. Sure, go ahead, Gail.
Yeah, back to the scholarship announcement. And I think it's great. And ours was won by a young man up in Sylmar. And it's great. I mean, I was a former special ed director, and he's driving a bus part-time as he puts himself through college for handicapped kids. So I think that's fabulous. The point I want to make is not a single San Diegan, and I got this from someone in the ARRL, not a single San Diego youth applied in our entire county. And if we include that Imperial County with us, not one single student applied. So please, let's all endeavor to get the word out and do better when these two scholarships are earmarked for San Diego youth.
Yeah,
Comment.
Thank you, Gail. Go ahead, Charlie.
Comment. I personally, in the period of time that we were trying to figure out what was going on with our scholarship, I personally contacted 4 high schools, the principal's office, never heard back. So sounds to me like maybe the kids aren't so hard up after all.
Yeah, I don't want to belabor the point, but it's got to get through the amateur radio community and clubs and robotics clubs and ham clubs and things like that. The principal is just going to leave it on their desk, unfortunately. You might reach out to some guidance counselors, but I think we've really got to go directly to the youth.
Okay, thanks, Gail and Charlie. Any other announcements before we move on to reports? Okay, we'll go a little bit out of order. If Glenn, if you're ready for membership.
Sure. So we currently have 160 current members, and anyone who needs to do it should check the scope, and there's a listing in there of memberships that have lapsed, I think since the beginning of April or beginning of March, and also if your membership is going to lapse between when I did the report last week and 2 months out into the future. So just go on there, your call sign's there. If you click on your call sign, it'll take you to the website, and it'll show when your membership lapsed, and you can click once more and renew, get back on, rejoin. And I think I was busy on the phone when Matthew KN6WX introduced himself as a first-time visitor, and he's actually a new member. He joined back in on the 12th of July, and he's a general class. And also we have Eugene KM6NRW, also a general class that joined on the 25th of July. And I think that's all I've got.
Okay, great. Thanks, Glenn. And then Mark, I will turn it over to you. I don't see John on, so I guess it's just you. And then you were going to have, after you give your report, you were going to talk a little bit about the conditions leading into our topic today up on the hill. Go ahead, Mark. Mark, we don't hear you. You're muted.
How about now? Can you hear me now?
Yeah, we can. Yeah, at least I can.
All right.
Yep.
Thank you. All right. Yeah, somebody was putting out a lot of background noise and kind of funneling me off. Okay. Well, first we should start with John came back from the mountain last weekend. That's a good part. He worked on the 6-meter repeater and is still unsuccessful. Unfortunately, Russ, we do have a 50 megahertz repeater, but it's pretty badly crippled. It's probably about 90% noise and 10% signal, so it's pretty bad. But everything else is up and running. Charlie wanted to talk to me about Echolink. So I have been running Echolink quite a bit for the last few days or so, and also got hold of Bernie and checked the logs. And Echolink is up and crawling and has been and is working real well. Charlie, I think the problem you might be having was, and this is for everybody, when you get on to 447 to use Echolink, you have to hold the touch tone keys down for just a little while to get the DTMF to accept it. In other words, you can't just beep, 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 beep. You got to hold each one for like a good half a second.
Yeah, I know, it's working. Yeah.
Okay, very good. And then with regard to Mark and his infamous Wires X problems, as you guys know, I had Wires X running quite nicely. It was running on a $6,000 Alien system, which burned up a hard drive, solid state drive, and a RAID array. So rebuilding is kind of a pain. So I've gone to the other end. This is my new keyboard for the new computer. This is the new Wires X computer.
You know, it's not going to work very well if it's not plugged in.
Yeah, but I couldn't show it to you if I plugged it in, right? Anyway, so I will be.
Isn't it wireless?
Well, some of it is. Anyway, yeah, it's all wireless. The transmitting the electricity is the challenging part. Anyway, wireless power coupling. Anyway, so Wires X isn't dead. It's just limping. Anyway, finally, with regard to our presentation that we're going to be doing probably, I assume, right after this, When I was up on the mountain, I fixed several things, including dampening the noise between 146730 and 147030, the cross coupling. I've got a little bit more to do. Some of it came back. Seems now I've got it to the point where if it's cool up there in the repeater shack, it works fine. If it gets hot, I still have a little bit of a problem. Anyway, so I'll go back up again, but as I was saying to Kristen, because 146730, I'm sure all you guys know, our favorite repeater, its sensitivity is down and you hear noise on it now. So I disconnected the repeater right as it comes out of the recirculator. So it goes repeater, recirculator, filter. I got it after the filter. Then it goes out into a series of tune cavities and up into the antenna. So I disconnected it right out of the filter on the recirculator and measured the SWR. And on frequency with a really good network analyzer. And on frequency, the SWR was 1.47 at our receive frequency. The problem is that those cavities have been up there under that table for 20 years. And they're really nice tuned cavities, but they tuned down to 1.04 SWR, about 300 kilohertz above our frequency. So instead of 146.730, they're tuned about 147 roughly. So they've drifted off, and it's a pretty complex cavity system. So it was put in there. Everybody remembers, hopefully, Art McBride. He's the guy that they were tuned at the factory by the manufacturer, and Art whipped it all up, and I'm just kind of a little chicken about playing with it. So I've been reading manuals. If you guys know the acronym, Charlie will. It's an old Navy acronym, RTFM. Anyway, so I've been reading manuals on how to retune these cavities, and that's my next task up on the mountain. All right. Anything else for repeaters, Echolink, wires X, or any of the technical stuff? I'll tell you what, I'll mention one more thing, and that is our little neighbors who have moved in with us, which is the East County Repeater Association, ECRA. They operate 147030, and they have a backbone link from that, is it that one? Yeah, it's that one, over UHF to another mountain. And they have just gotten their remote base HF system up and running. So you can now control an HF base station through the repeaters. So they're getting ready to replace their repeaters, but they've got that up and crawling now. Is there anything else?
Nope, I think that's it.
I'm going to go back into the woodwork.
Okay, great. Okay, so Charlie, I'm going to come back to you for just a second on the program that we had to reschedule for next month. So that next month's program, if I'm not mistaken, that's on the Russian woodpecker. Is that right, Charlie?
Indeed, that is correct.
Okay, so it was originally scheduled for this month. Some unforeseen circumstances came up and that had to be rescheduled by the presenter. And so Kristen was kind enough to jump right in and cover this month at the last minute. So thank you very much to Kristen and to Charlie for arranging all of these meetings. With that, if there's one last call for comments, questions, announcements. Okay, introducing your board. Mark, who you just heard from, KF6WTN, is your repeater site and technical chair. Your scope editor is Keith, KM6CXW. your director, Greg K6WX, your other director, Joe KB6NMK, your membership chair, Glenn AI6RR, your treasurer, Tom W0NI, your secretary, John WB6IQS, your vice president, Charlie NN3V, and I am Joe, your president, K6JPE. And with that, we will turn it over to Kristen for our presentation on SWR. Who cares? Thank you, Kristen. Is that, and then that's K6WX.
That's right. Thanks, Joe.
All right,
And,
thank you.
thanks.
And unfortunately, I'm going to bow out for the evening. I have family stuff, so enjoy the presentation. I will go catch it later on the YouTube recording. Good night and 7-3.
All right, well, I guess I'm up here. So let me arrange to share my screen. Hopefully that all works. Yeah, here we go. There. Yeah, can everybody see that? We're good?
Yes.
Yep, you're good.
Yes, indeed.
All right.
Absolutely.
All right, so let's let that go full screen. Okay, so tonight we're going to talk about everybody's favorite topic, standing wave ratio, and see if anybody really cares about this thing. So people always ask me about this. You know, I run this, I've been net control on this net that goes on around here called the 9 AM Talk Net. It's been going on for about 30 years now. And I'm net control on Fridays, and a lot of technical stuff comes up on Fridays. And people ask me questions about SWR and what's going on with their antennas and things like that. So among other things, and some of you who saw my grounding talk, realize I like to kind of take on these things that everybody thinks should be a certain way and see if I can break them down and help you understand them better and maybe dispel a few myths about them. So let's start by thinking about what is SWR. Is it a breakfast cereal? No, I don't think so. Is it a floor polish? No. Is it a nifty way to say slower? Perhaps. An obsessive compulsive disorder? Definitely. So I'm sure you all know people like that. But more precisely, it's called standing wave ratio. Some people call it voltage standing wave ratio. It doesn't really matter that much. It's more about the wave mechanics. But you know, when we start pinning numbers on it, we have to use units. So we'll talk a little bit more about the exact definition of this thing as we go along. But I wanted to at least give you an intro as to what it's called. Now, you guys all know this person, right? 1.12 to 1 means the whole system has to be torn down and retuned. I know a guy like this who, you know, every time it rains a little bit, he's out there and saying, oh, no, my 80-meter vertical is completely detuned at 1.1 to 1 or something like that. The other thing that you see a lot is that resonance is 1-to-1 SWR. And I'm sure you've heard this, right? Well, I'm going to show you that that's not exactly the case. The other thing we hear a lot is that power is wasted, right? So if you have a 1.5 to 1, 1.8 to 1, you're throwing all this power on the floor. And the other one is, of course, you know, I just feel better when it's 1 to 1. Which is kind of the craziest one of all, but you've heard it, right? I've certainly heard it. Now, this is both like and unlike ground is a myth. If you remember ground is a myth, I really assert that there's really no such thing as ground. It's a very confusing way to look at the world when you put it that way, but SWR actually has some uses, and it has a nice clear definition mathematically, and when properly applied, can be a useful quantity. It's not a myth. It's something that we can actually use, but the problem is it's often over-applied. So let's dig a little deeper into this. In order to dig deeper into SWR, we're going to have to understand wave mechanics a little bit, and we're going to do that in an unconventional medium to see what it is, and we're going to look at how we calculate it and what kinds of things we're measuring with this and what parts of it to care about and what parts to potentially not care about. So we're going to start with wave mechanics. This is the study of waves. This is if you took oh gosh, I don't know, maybe first semester physics, maybe second semester, we talked about wave propagations. And what is a wave? A wave is basically some kind of disturbance in a medium or a field, if you want to do it mathematically. And it can often be an oscillation, although not exclusively. And I'm going to show you some examples of what that are not just simple sinusoidal oscillations. And these waves can be in a number of different things. They can be mechanical waves in many different media. They can be electrical, they can be quantum waves. We describe a lot of quantum phenomena in a wave-like way. And now, as we've seen with the LIGO instrument, gravity waves, which we believe we have detected. So simple wave motion starts with a very simple set of equations. It looks like a sinusoid. Most of the time, the governing equations look like this. The ones on the top are the real parts. So some amplitude A times sine omega t plus phi. Omega is the radiant frequency. That's 2 pi, the conventional frequency. And wavelength, as you've defined it before, v over f, where v is the velocity, which might be speed of light for electrical stuff. And phi is the phase, and which we use to just kind of, if we have two things that are the same frequency, they might be slightly off in phase. And of course, on the bottom, we have the complex version of that, e to the minus j omega t plus phi. That gives us the complete complex description, which is actually easier to work with in some ways if you can bear with the imaginary numbers there. Now, mechanical waves, I like to start with because they're really easy to understand. They're in the real world, and you can try this stuff at home. If you get the right kind of rope, if it's got the right amount of tension, you can actually take that piece of rope and move it around. I was doing this in my yard with the garden hose a couple days ago. If you get the right amount of tension on the rope or the right amount of flexibility in the rope, you can actually propagate waves down that rope if you do it right. And the speed is such that you can watch the waves move, which is really cool. And the coolest device that I've ever seen to do this is called the Shive Wave Machine, which you see in the picture here. And I tried to buy one because I thought it'd be a great prop for this talk, but they're unobtainium. You just can't get them anywhere. There was a big one at MIT. If you've ever been there in 26100, it's like the biggest lecture hall at MIT. And it just like runs across the ceiling, but sadly I never really saw it in use, but they're really fun to watch. And I have a little video to show you later of how they work. So traveling waves, let's talk about those. When we have an impedance match, and we'll talk about what that means a little bit later, we get traveling waves. And yes, there is an impedance in a mechanical system, and there is a notion of matching in a mechanical system. And when we have a matching such that all the energy moves along the medium, we'll talk about what that means a little bit later, we get these waves that appear to travel. But in reality, they're just kind of propagating in the normal way. They move, in this case, from left to right, because that's the way we drew the graph. But they just kind of move like this without any kind of stationary parts of them. And we call them traveling, of course, because the peaks and valleys are all moving across the medium in a regular way. Now, we have to, if we're going to talk about waves, we have to talk about the notion of superposition. Now, if we have multiple sources of energy or multiple sources of wave perturbation, since it's a linear system for the most part, these waves sort of operate independently, and they add and subtract. They're kind of overlaid on top of one another. So if I show these two pulses like this, you can see the pulses move in towards the center. We have kind of the big one and the little ones appear to exchange from each other, but it's like they mush together and then they come apart in exactly the way they were before. So there's no kind of bad interaction that modifies them along the way. This assumes that the whole system is linear, but they kind of almost pass through each other in a ghostly sort of way. And on the bottom, you can see that if we have one wave that's stationary relative to what we're looking at and another one moving, we get sort of an addition and subtraction effect that causes the waveform on the bottom, which is the resultant one, to appear to kind of flip over, go to zero and then reappear and be sort of stationary and sort of not. So you get these interesting effects because these waves can be overlaid on top of one another without modifying them. A useful way to think about this, I think, at least when I learned this stuff, was the idea of boundary conditions. So what happens at the end of something, or like when it transitions from one medium to another? In this case, we're going to look at ropes. So I'm going to, in these pictures, essentially take a rope and I'm going to flick it. And when I flick it, it's going to cause a little pulse along the rope. And in one case, we have a free end. So I think that's the first one up here. So you can see the rope gets flicked and the free end moves up and down. So in the free case, we have motion, but no tension. So it's able to move to the end. And you see what happens is it reflects back with the same polarity because we match that boundary condition. So when we get the peak of the wave over there, it's deflected up. And then in order to stay consistent, it comes back in the same way. Now, if we hold the rope stationary on the right-hand side there at the top one, you'll see the pulse comes in, but flips over. And this is because we can't have any deflection there. And we have to transfer all of that momentum back the other way. And the only way to transfer the momentum back and satisfy all the physics stuff like conservation of momentum, conservation of energy, is for it to flip over like that. So you can see that we get a different reaction. And if you're thinking out there about what I might talk about next, you can kind of think about open and shorted transmission lines, because that's where we're headed with this. Now, of course, there's also many points in between these two extremes. So I've showed you kind of the piece of rope with nothing constraining it and the piece of rope that's completely constrained. Let's look at some different constraint points. So in this case, we'll have a pulse that goes down and it goes into a different medium. So we have a rope that's, for example, very small and light into a one that's a bit thicker and heavier. So you can see the pulse travel down and it's like it's partially held. So part of it flips over and comes back and another part continues onward with the same polarity. So this is a combination of a kind of held steady and released examples that you saw on the last slide. And again, energy and momentum are conserved through this. Here's the opposite case where we have a thicker, heavier piece of rope and then a lighter one. So you see stuff travel across and then some travel back. So these look like little reflections. So the pulse might come in and it might reflect back in the same polarity or opposite polarity, depending upon which effect we're moving from and to. Now, for standing waves, whenever we have a so-called mismatch, which we'll talk about in a couple of minutes, we have waves that are propagating from left to right, and then some that are reflecting back, just like you saw on the last slide, and reflecting back in the opposite direction, and you're getting the superposition of those two. So you can see this here. We have on the top one wave going what we would call forward from left to right. The other one is what we would call backwards from right to left. And the two superposed on top of one another give us this sort of stationary pattern. It's not that the waves are stationary, but the pattern is stationary. And what we see is that the envelope of that pattern gives us this standing wave notion. And so you can kind of see it, although it's still moving around. But if we look at the envelope, it's seemingly staying right there. And that stationary pattern is what we call a standing wave. Now, what's the standing wave ratio? Well, we do this in ham radio all the time. There's a mathematical description. We have this notion of a reflection coefficient, which is a simple algebraic combination of some impedances. And then we calculate the SWR from the magnitude of that reflection coefficient. But it's kind of the ratio of the peak to the trough of the envelope of those standing waves that we saw before. And this, of course, applies to mechanical waves too. And we're going to see an example in a moment of how this happens in the mechanical world. But this is the rigorous definition if you want to know. And this set of equations can apply even for mechanical systems, not just electrical systems. And there's also a thing called a characteristic impedance. So we have media that these waves are moving through. You saw a piece of rope, that's a form of a medium. And it can be also capacitors and inductors. If we think about a transmission line, an electrical transmission line, it's like a series of capacitors and inductors. We can actually break it down that way. And it's called a lumped element model. And in the mechanical case, it's the ratio of a couple of parameters. It's the deflection and the tension in the rope. And in the transmission line case, electrical transmission line case, it's voltage and current, or electric and magnetic fields. So I'm going to run this little animation that I stole off of YouTube, and you'll see a little bit of how it works in the electrical case. You can see a contact come down, we apply some voltage, and we're going to lift things up as a representation of voltage. And you can see that it kind of propagates down, charging up those fields as it goes. And notice something really interesting. When it gets to the end, you'll see that it gets to the last set of elements, they go up, and then it has to kind of come back because there's nowhere for the energy to go. So the energy can't be transferred. It was transferred very nicely from element to element in the earlier ones. But now it's kind of reached the end and there's no easy place for it to go. So it has to stay within the system. And this is how it begins to come back the other way. Now, we talked about matches. I alluded to it before. This is going to be an example of a match. We have a nice animation here, or a video of a shive wave machine. So if we have a rope, that energy is transferred or absorbed down the length of the rope. So we have a certain amount of deflection and tension that results in work done on the rope that's equivalent to energy by the work energy theorem. And it moves until it gets to the end. And if you watch this, you'll see the wave propagate down. And when it gets to the end, it is so-called matched. And you'll see that energy come down to the end and just disappear. You can see that right there. You see how those waves just went away. And what happened in that case is that there was just enough damping on the end there to absorb all the energy that traveled down. If all of that energy wasn't absorbed, it would have come back the other way because it has to go somewhere by conservation of energy. So it's either absorbed or transferred to the next stage of the system. So if we watch this one more time, I think I can get it to animate again. You can see that it's being propagated from one of those sticks to the next stick slowly down the system. And then at the very end, that energy is turned into heat, basically. There's probably a dash pot there that just matches the system perfectly. So when you have that condition, we call it a matched condition. But you're probably about now saying, why am I getting a physics lesson instead of talking about ham radio? And that this is not radio, but it really is. The things we're talking about are essentially this tension and deflection are very similar to voltage and current. I mean, you could flip them over. I chose to think of them this way, where deflection is like voltage, tension's like current. And we have the same kind of constraints we often have. So we have a transmission line, and at the end of that transmission line, it might be open, it might be shorted, we might have a 50 ohm resistor there, we might have an antenna. So I wrote that it's a great analogy, but it's actually more than that. It's actually equivalent. The same wave mechanics apply exactly to both cases, both the electrical and the mechanical case. When we do it in coax, it's the same sort of thing, except it has a bit more dimensionality to it. It's a lot like the rope, but it's just a little more complicated, but it uses the same principles. So we have electric fields and magnetic fields propagating, and it looks a little complicated here. You can see the on the right-hand side, the blue ones are the magnetic field, and the red ones are the electric field. And as it propagates down, it has a characteristic impedance, which has to do with this ratio of voltage and current, or electric and magnetic energy. And that propagates down from, like if you slice the coax into little elements, it propagates from element to element perfectly coupling the energy as it goes down to the end. What it does at the end depends on what's sitting out there. You know, if it's an open, a certain thing happens. If it's a short, another thing happens. If it's a perfectly matched load, it transfers all the energy out. So open wire feed lines, the same kind of thing. It's just a different geometry. It's a little easier to think about open wire feed line because you know, you have all these circular fields. In the case of coax, it's a little harder to calculate sometimes, easy to measure. It has what we might call as hams an atypical characteristic impedance, right? We've seen open wire line that's 300 ohms, 400 ohms, more, less. And we can actually measure things like standing wave ratios by measuring those fields directly. We can light up light bulbs and things like that, but it's still the same concept, either one. To talk about these waves and kind of think about them, we use this cool device called a Smith chart, which is kind of a weird twisted circular slide rule of sorts. And I'm going to talk about it, although probably people are just thinking, why am I looking about Smith charts right now? But the reason I want to talk about them is because they teach us something about SWR that I want you to know about. So we use them to kind of estimate impedance as we move down a transmission line. We can use SWR as one input to what you see here. Smith charts are independent of the system impedance. You want to do it at 300 ohms, you want to do it at 50 ohms, you want to do it at 10 ohms. It all still works just fine. And they're really not that hard to look at. And what they are in mathematical sense is a conformal map of gamma, which is that reflection coefficient. Conformal map means that the angles are preserved. So let's look into this a little bit deeper. So we have this notion of prime center, which you can see in the top diagram. The center little yellow dot there is prime center. Then we have resistance circles that radiate from the right-hand side. So you can see them at different values that come out from there. And then we have reactance curves. And you can see the reactance curves on the bottom left. The bottom right overlays the reactance curves on the resistance circles. And when we pick a point, we define an impedance there. So anywhere where, for example, one of those reactance curves crosses a resistance circle, we can say, well, that's an impedance. And there's an example there of 0.5 plus J1. And rotation, we rotate around prime center. That tells us how far or close we are to the load or the generator. And we change our directions based on whether we're talking about loads and generators anyway. But the whole thing is normalized. So right at the center, you can see it says 1.0. 1.0 is your system impedance. So if we're talking about a typical ham radio system, it's 50 ohms. So we'll say that 1.0 represents 50 ohms. And if it's 0.5, well, that represents 25 ohms, for example. Here's a complete SWR or a complete Smith chart with all of that stuff overlaid with a SWR circle. So it turns out that if you have a completely matched system, you'll be at that single point in the center, no matter how close or far you get from the generator. But if your system is not well matched, you'll find that the points, the impedances you encounter as you move down a transmission line will lie along that SWR circle. So if you want to, for example, find an SWR, you start with some impedance, you scale it, the system impedance to Z0. That's 50 ohms, so 50 ohm thing. You plot that point. Now you make a circle centered at that prime center, and the SWR circle is the radius to there, right? That represents the SWR. All equivalent impedances lie around that circle, and gamma is the radius of that circle. So the SWR itself intersects on the right-hand side. So if you can see those little markings, they're really hard to see. On the right-hand side from prime center, where it intersects on that axis, that's the SWR. So if you have a 3-to-1 SWR, you just go to that point on the right and you draw a circle starting from prime center as the center of that circle. And then you get all these equivalent impedances as you rotate around. If you want to find impedances, it's the same sort of thing. You do it the other way. You can plot the point, you get on the right-hand side to get with the SWR, you put the SWR on the right-hand side, you make a circle centered at 1. And then what you find is that all the points in the circle have the same SWR. This is really important. So what I'm saying is that if you have like a 3-to-1 SWR, all points on that circle are 3-to-1 SWR. An infinite number of different points represent 3-to-1 SWR. That's an important concept. But who cares? I mean, why do you care about all this crazy stuff? Well, it shows us something. That's why you care, I guess. It shows us something that's on the Smith chart, shows us that SWR is a degenerate measure. It's something, it tells us something about a system, something about the energy that's transferred around, but not everything by any means. There is an infinite set of impedances that satisfy that SWR. We know that the actual impedance of the system is not that important. All of this is shown in the math. So we know something, but we don't know a whole lot. So what we observe is, of course, the absolute load doesn't really matter. It's just the relative load. Resistance is resistance. It's the same no matter where you are, 50 ohms, 300 ohms, whatever. It's all on that, on the real axis there. The wave mechanics are exactly the same. If you change the system impedance, you want to make a system at 300 ohms, nothing about the wave mechanics changes. It's all the same. And that energy propagates. It moves around down a transmission line to a load from a generator, and it ends up either as propagating fields, mechanical energy, or heat, one of those three things. There are some more subtle ones, but those are the three ones that we care about today. So I've been talking about this thing called the generator. We have a generator in our system. We call it a transmitter. This is my FT100 that I salvaged from eBay that required a fair bit of reworking to make it work right. There's an equivalent circuit that we can talk about with this generator. And I think there's a lot of confusion in the ham radio world about what this generator and the equivalent circuit look like. These things are designed for a certain system impedance. Whether it's tubes or transistors, there's a certain system impedance that they're really happy with. And the question to ask is, can it deliver power? Most of our transistorized amplifiers and rigs are designed around a 50 ohm system impedance. But if you have a rig with tube finals, or if you have a tube amplifier, it's not necessarily designed for 50 ohm system. It's designed to whatever you tune the load circuit to. So you tune up the plate and you tune the load, and you tune that load in with a matching network that allows it to couple energy out. But the transistor ones tend to be more fixed than that. Now, I'm going to take a brief diversion here because I want to talk about something called the maximum power transfer theorem. And this is something I see misapplied all over the place. And that's why I want to take this aside and talk about it. And I see it misapplied a lot when it comes to things like SWR and matching and that kind of thing. So the maximum power transfer theorem sort of states that the load and source impedance have to be the same for the maximum power transfer. I'm sure you've all heard that before if you've dabbled in this stuff a little bit, but I find that it's abused a lot. And it has an assumption baked in here that's really important to understand. It assumes that that source impedance is a fixed value and you can't change it. So it's not symmetric. If you can change that source value, I can choose a better source value than what the load would be. So let me give you a simple example to work with. So this is a degenerate case. I'm going to try and transfer the maximum power into a fixed 50 ohm load, just a resistor. And I have just a DC power source, okay? So just to make things simple. And I'm going to say up front that I'm going to be able to change the source resistance. So let's assume that we have 50 volts for the voltage source and that the source resistor is 50 ohms. And let's calculate the power that I can deliver to the load resistor. So it's really simple. Power is V squared over R. And I just did a little algebra there and I came up with 12.5 watts. Okay, not bad. But I said I can change that source resistor. So I'm going to choose to change it to 0 ohms. So if I change it to 0 ohms and redo the algebra, look at the difference. I can get 50 watts into that resistor. So clearly, for the general case, the two being the same is not the maximum power transferred. It's only the maximum power transferred when I have no control over that source impedance. Now, transmitters, what do they look like? Do they have a 50 ohm resistor in them? No. No transistors. The transmitters that we use don't have any 50 ohm resistors sitting there to make it look like a 50 ohm source. They look a lot more like voltage sources, although they're kind of complicated. And they're designed to kind of match a 50 ohm load, and by match meaning just deliver power into it. And if the power is delivered out of there, it's a really happy camper. Sometimes some power comes back and gets re-reflected, that kind of thing. But it really likes to see a 50 ohm load. So they put a little matching network in there to try and get whatever the complicated transistor impedances look like to couple well into a 50 ohm system and not stress the transistors unduly. But you know, it's really complicated how the impedance changes as we go through each individual cycle of the transistors operating in the output. So what the transmitter really wants, and this doesn't matter if it's tubes or transistors, is that they just want to be happy, just like all of us, right? We just want to be happy, so does your transmitter. And we want to keep those finals nice and linear. We want to keep them efficient, and we want to keep them from burning up. And so we designed the system such that those devices are happy, and any other componentry you have in the power supply and all that stuff is really happy driving a certain load that the designer designs against. So in most cases for ham radio, it's 50 ohms. In other systems, it's 75. In others, it may be more. Now, let's talk about real world transmission lines too. They're not perfect. Transmission lines have their own sets of problems. They have different kinds of losses in them. They have resistive losses. They have dielectric losses, and that comes from flipping the dipoles back and forth in the actual material in the gap between the two conductors. There's leakage losses too, so the fields may not be perfectly contained within the transmission line. And when we have a high SWR, remember that's kind of this ratio of the peak to the valley of these standing waves that are caused by stuff that goes down and reflects. So we can get high voltage and high current at different points in the coax, and that can mean heat. So if we have a lot of current, we have a certain amount of resistivity, the coax is going to get hot. If we have really high voltages, the electric fields are going to be high, and we can get a lot of dipole flipping, and we can heat up that dielectric. So they have a certain amount of loss, and that loss is actually proportional to the standing wave ratio because it's stressing the material. So in coax, we have even more loss than open wire feed line, and that means that's mostly because we have this dielectric that's in the coax and the geometry, but it's a lot has to do with the field concentration in the dielectric in that particular geometry that causes us to have more loss. And in particular, in different kinds of coax, we have different amounts of loss, and it depends on dimensions of material and all sorts of stuff. But the ARL has a nice little matched loss equation that's handy for figuring out what the loss will be like. And I've reproduced it here. I'm not going to go into the explanation of all the details, but the idea is that if you have a piece of coax and it has a matched load, in other words, all of the energy is being transferred down the coax and moving on to the next part of the system, and you can measure that loss, I can give you an equation that will roughly express what the loss would be if the SWR is not matched. So if you give me a different SWR, I can tell you kind of what the losses will look like. And this is not a perfect model, but it's a pretty good one. So here's an example. We have some generic coax, and I have a 1 dB match loss. So if I take this coax and I hook it up and doesn't matter what the length is. Let's say it's 100 feet, although this is pretty optimistic. So over a 100-foot run and it's matched and I get a 1 dB loss. If I have a 2-to-1 SWR, I can add 0.2 dB to that. 5-to-1, I can add another dB. 10-to-1, I can add 2.2 dB. And this is a reproduction of a chart that you can find in a QSD article. I think it's also maybe in the either the antenna book or the handbook where you can find this. But with this graph, and I just looked at the graph here, you have these lines of constant SWR, and the line loss, the match loss is on the x-axis, and the additional loss you can read off of the y-axis. So you can see that when the SWR goes up, you have a loss, and it could be somewhat significant or not. You know, in this case, unless you're doing moon bounce, or building a repeater for that matter, it's probably not such a big deal. So you have to look at that and see if that matters to you. So we have a transmitter, we have loads, we have transmission lines. The idea is to get energy out of that transmission line and into the load. And in order to make that happen, we often have to match to make the transmitter happy more than anything else. We have choices about where we can match. We can match close to the transmitter, which is an easy thing to do, and take the feed line loss hit, right? So we match at the transmitter, we have some higher SWR in the feed line, we look at our match loss equation, and we say, well, we're gonna throw away a couple dB, or we stick a matching network out by the antenna or out by the load. And that is the most efficient thing because we have basically a matched load at the end of the coax. But of course, getting that tuner out there can be a pain. So we have these matching networks that help us do that kind of thing. They kind of null out the reactance, or they basically make a complex conjugate thing that kind of nulls out the reactive portion and can actually adjust the resistive portion so that we can make the transmitter happy again. So if we see some wacky impedance out at the antenna, we can use this matching network to pull it in and make it mimic 50 ohms to some degree of accuracy. It won't be perfect. And of course, these things are not perfect either, these networks. They have their own sets of losses. This particular one in the picture is a pretty efficient one because it uses air as the dielectric and air as the magnetic element to might increase the magnetic permeability. So those are pretty efficient. When you start using dielectrics, you get the non-air dielectrics, you get the dielectric losses, again, the dipole losses. And you put ferrites in there and you get nonlinearities. And you also get the same kind of problem with these dipoles flipping that causes heat. Now, what about the antenna? The antenna is part of the system. Our ham radio life wants to just get energy out of that generator, out of that transmitter, down this transmission line and out to the antenna. And we want to efficiently couple it into that antenna. And we know that our transmitter likes 50 ohms, so does our coax. But most antennas are not 50 ohms. If you connect up your dipole or you connect up your monopole and you're seeing a 1-to-1 SWR, which means that we're transferring all that energy out, something's a little bit wrong. You're actually throwing away some energy somewhere in the system, usually resistance somewhere, either to the dirt or to a tree or something like that, where the fields are burning up a little bit of power and turning it into heat. Yagis without any matching network are very low impedance, you know, on the order of 10 or 12 or 13 ohms, something like that is pretty common. So most antennas are just not this chosen system impedance or some other impedance that's dependent upon the geometry and the surrounding terrain. So we want to try and match that in a way that minimizes our losses in the coax, if we care about them, and makes our transmitter happy. But the more important thing to worry about is, you know, the pattern of the antenna and making sure that it has a pattern that's useful for us. So what do we really care about in all of this? I've done a lot of talking, but what are the things that really matter? The things that really matter in the end, at least in the case of most amateur radio operations, is to make the transmitter happy. If the transmitter is happy, it'll run nice and cool, and you won't blow up the transistors. Everything will be hunky-dory. We want to account for the loss in the feed line and decide whether we care about it or not. So if we have people will ask me, well, I have this, 1.2 to 1 thing, and I say, well, how long is your transmission line? And they say, well, it's 15 or 20 feet. And I say, forget about it. It's not going to do anything really interesting there. Just don't worry about it. If it's a long run, maybe you should think about it. If you're operating at VHF or UHF or even higher, that long run may be really a big downside. You may have a lot of loss. But the really important thing is to decide whether this matters to you. Can you afford to throw away that couple of dB? It may save you a lot of work if you can. And the most important thing of all, of course, is to have fun on the radio. That's what really matters in the end. So if you want to learn more about how waves propagate and how SWR works and things like that, I recommend, of course, the ARL handbook is a great reference on many fronts. The antenna book's even better. It has more stuff on that. But if you want to dive deeper into the real meaning of this stuff, you can look on Wikipedia. There's a decent article there these days about SWR and a few cool ones about wave mechanics. But the real reference will be your physics texts. Just pull them down. I know they're all dusty sitting on the shelf there, but there's some good stuff in there that'll talk to you about how these waves propagate and how it works. And there's actually pretty simple math behind it. So I'll take any questions.
Well, our president has vacated, so I'm going to step in and play host. And so I'll say, does anybody have any questions for Kristen on this?
Yes, I do. NA6MB.
Go ahead, man.
Okay, I actually have three, a couple questions, a couple comments. Number one is, I noticed that label that said Kristen on it. Is that a Kristen antenna?
Actually, that was from a Calacuso party expedition, and that was my coax going to my antennas, yes.
Okay, great. The other thing is, the second one is about the voltage with a mismatched SWR. You can make your antenna look great to the transmitter with a tuner next to the transmitter, but I found out that that doesn't really help your antenna. I was, my R7 was out of tune a little bit, so I tuned it with a tuner, made the transmitter really happy, but when I put about half the power that the antenna is rated for, it arced over at the antenna and blew it up. So be careful of just making the antenna, the radio happy and not worry about the antenna, because the SWR in the line, obviously at the other end, was wrong and it had a very high voltage. And the last thing
we
is,
always have to be, well, let me react to that and then I'll take your last one. But you always have to be conscious of the fact that, for electrical circuits anyway, power is voltage times current. And so if you change the balance, in other words, you change the impedance such that there'll be less current, there will be more voltage. The power's got to go somewhere. So yes, and that's what happens inside a transmission line as well. When you have big mismatches, that voltage goes way up and you can have arcing right in the transmission line. So yeah, you always have to be aware of breakdowns in any of these materials.
yeah, I was looking
power
at,
ratings for antennas are very flaky things. They're, they're derived by, hand waving.
I was lucky it didn't arc the coax and blow that up, because it's about a 75.
Yes, you were lucky.
213. It could have had a unknown where it is, open or short, based on burning it. Anyway, the last question is, if you go back to the Smith charts, you talk about a little bit the SWR circle, and then show the J plus and minus, and how you can fix that with impedance at the antenna or in the system.
Yeah, so the one thing you can do with a length of coax or a length of transmission line is move yourself around on that circle. So if you're at some point, you know, let's say in the upper right-hand quadrant, and your matching network would do a better job in the lower left-hand quadrant, you can just add a piece of coax and move yourself around on the circle and have your matching network work better there. Matching networks, you know, of course, they're limited. They have a certain amount of capacitance, a certain amount of inductance to play with. And the way they're configured, you know, if it's an L or a T, changes what the limitations may be. So you can move yourself around on the circle. You can't change the SWR except that, you know, it changes a little bit by losses in the coax. It starts looking better and better as you get farther and farther away because the coax is lossy. So it starts to spiral in towards that prime center in the Smith chart. But as you move in the SWR circle, you're not fundamentally changing anything. You just may be making something more advantageous for the matching network.
Right, but you could put a fixed L or C or combination somewhere in the system and not have to have a tuner for a fixed frequency.
Oh, sure, sure, sure. Yeah, I mean, that's what a tuner sort of is an L or a C or a combination and an L network of an L and a C. Or you can make a T network or whatever with of fixed values that makes life easier, sure, and matches even. And many people do that. But, you know, keep in mind that, you know, if it's just an L or a C, it might or might not match because remember, monopoles are not 50 ohms, nor are dipoles, nor are Yagis or anything else. So are generally not 50 ohms. I'm not saying never, but generally not. And so if your matching network with a single element, like an L or a C manages to match it, chances are you've got losses elsewhere.
Anybody else have any questions? Hello?
I'll just make a comment.
Yeah.
This is Glenn, AI6RR. I've learned a lot in the last few years with a piece of software called SimSmith by a ham named Ward Harriman. And because it shows the generator on one end and the load on the other, and you get to pop in whatever kind of elements you want. If you think you need a shunt inductor, you put that in and you can see what it does to remap you on the Smith chart. And it takes care of playing with different impedances. It's a lot of fun. SimSmith.
Oh, that's cool. I like it. Yeah, I think I've heard about that.
Well, okay, this is KF6WTN. And one of the things that can always be an issue when you're doing these types of meetings is becoming overly complex. And, you know, if you read Stephen Hawking's book, Brief History of Time, they told him that every time he added equation to his book, he would half the number of readers. And I think you did an excellent job of presenting this without going crazy into the math. And I appreciate it. Thank you very much. This was a great presentation.
Well, thank you. I'm glad I hit the mark there. That's something I always try to do as best I can.
Yeah, well, thank God you you weren't teaching my electromagnetic fields course.
A comment from K9Q. This is really the same thing as power factor in an AC power network, which is something a lot of people don't understand. But in principle, it's really the same thing. You've got power flowing back from the load back towards the generator, but in most cases, it doesn't really cause any harm, except that it can increase the losses along the way. And it's the same thing here with transmission line losses going up when the SWR isn't one-to-one.
Yeah, you can certainly think about it that way. And, you know, the question becomes then with power factor too, the same thing is like, can you do any work with that? And when you have that phase mismatch between voltage and current, you can't do work. And by work, I mean the physics version of work. But yeah, there are a lot of similarities to that.
Right. Yeah. I mean, the thing is to remember always that energy never disappears. It always has to go somewhere, even if that somewhere is heat. And that's such a simple rule that people often seem to forget in practice. You just remind them of that. Suddenly everything becomes clear again.
That's right. And, you know, you'll see that if you were actually able to measure the temperatures on things, which is a very hard thing to do, you'd see that things heat up appropriately, and that'll show you exactly how much energy you've lost in the system. But yes, energy must be conserved along with momentum.
Okay, I just got a note from NN3V that says, regret my audio is inoperative. So I guess Charlie is not quite there at the moment and working to fix it. So with that, I'm going to ask if there are any last questions. Going once, going twice.
Thank you, Kristen.
Thank you for a wonderful presentation. If you guys want to pass this along to anyone, keep it in mind that this is archived on our website, and people can go back and study it and try and figure out anything they might have missed when it was live. With that, I guess I've never closed a meeting before, so I'll ask if there are any final comments. Going once, going twice.
One comment, just one comment.
Okay, yeah, go ahead, Mike.
Back to the scholarships, I kind of want to acknowledge Phil Karn. I can't remember his call sign at the top of my head, but he put in a lot of cash and matched our scholarship money this year for the person that received it. So KA9Q. Thanks, Phil.
Awesome. Hey, you're welcome. Remember, it's not my cash personally. It's the Amateur Radio Digital Communications group. I happen to be president at the moment.
You did the work and got it to the ARL. So
that's right. Yeah, we matched each one of the league's scholarships 1-for-1 this year.
Yeah,
next year our plan is to create new separate scholarships with different rules.
Yep, great.
Total amount would probably be the same. So by all means, get people to apply for them here.
Yeah, San Diego County kids need to apply.
Right. And any way we can help with writing anything up about the criteria, just call me.
Okay.
All right. So once again, are there any final comments? Oh, Charlie is sending me a 73 and 88 DE and N3V. I think he's reached his fun limit. What can I say? It's almost 9 o'clock. All right. Okay, at that point, I'm going to close the meeting, turn off the recording, and I